Hello there, thank you for clicking into this video. I've been here waiting for you. So let me guess, you're curious about protein and protein characterizations, right? Nice, I'm glad you do, because that's what we're gonna talk about today. Specifically, I would like to show you how we can access protein hydration and structure in one single automated measurement. My name is Maria Ma. I'm the application scientist and market development manager at RedShiftBio. Let me walk you inside. And while we're walking, let me introduce you to RedShiftBio. At RedShiftBio, we have developed and launched a new technology that made structural analysis fast, automated, and robust with ultra sensitivity. The new technology is called MMS, which stands for Microfluidic Modulation Spectroscopy. Okay, come inside. So we actually have many videos that dig deeper into the technology and show its application range from preclinical discovery like lead optimization to formulation, process development, and all the way to QC. Please check them out on our YouTube channel.
So here we have summarized what MMS can do in one automated run. So first, stability by comparing before and after stress. Then aggregation. MMS will not only quantify the structural aggregation, but also help you distinguish the type of aggregation. For example, colloidal cluster in which the molecule is still well folded versus structural aggregation, in which case it's oftentimes irreversible. And thirdly, it quantifies the structure and the similarity of the structure between samples. And finally, MMS also offers the molecule concentration quantification. So our customers use MMS not only for proteins, but also other biologics, including conjugates, nucleic acids, AAVs, VLPs. So as exciting as it already is, today I will show you something even more exciting, which is that MMS can also provide some free additional data on top of all this. One of them is on protein hydration. And please let me further explain. So to showcase how MMS is able to do so, we compared lysozyme in different concentrations of sucrose, which is a widely used excipient in drug formulations to enhance the stability of protein molecules. Here we dissolve the lysozyme at 2 mg/ml in water with a sucrose concentration increasing from 0 to 16%. So our first observation was that lysozyme, being an alpha helix rich protein, increased its alpha helix content, which is its native structure, with the increase of sucrose concentration, and decreased its beta sheet content with the increase of sucrose concentration. It also showed that an increasing trend in beta turn from 0 to 8% sucrose, but then it dropped a little bit at 16% sucrose. So next, we quantified the overall structural changes. And to do so, we have two mathematical weapons. The first one on the left is by area of overlap. And the second one on the right is by WSD, or weighted spectral differences. Let me explain. So let's start with the one on the left by area of overlap, which is quite simple. We have one curve compared to the other, and we use the area beneath the curve that is overlapped between the two and divided by the area beneath the control curve. So using this method, here in the first column, we have the repeatability among the 3 replicates, which are all above 99%. And in the second column, we have the similarity compared to lysozyme in water with 0 sucrose. So here we see a slight change in the structure with the presence of sucrose. So the second mathematical weapon, WSD, is usually more sensitive. It is an integral of the distance between 2 curves, but weighted more heavily at the wave number where signals are stronger. Again, the first column is the repeatability among the 3 replicates, and the second column is the WSD compared to lysozyme in water with 0 sucrose. We see a trend of increasing structural changes as sucrose increases in concentration. Next, let's add protein hydration. So first, let me explain what protein hydration means. When dry proteins are exposed to water, they rapidly bind water molecules up to a maximum quantity, which differs for different proteins. This interaction between a protein molecule and a water molecule is oftentimes referred to as protein hydration, and it plays a crucial role in protein folding, stability, and activity. So in this figure, we're illustrating a protein whose functional domain is indicated by a black rectangle. And once the protein is dissolved in an aqueous solution, it is surrounded by water molecules thanks to polarity. When the domain is open, water molecules get inside, and once the domain closes, water molecules are squeezed out. This shows that protein hydration is important for collective domain motions, which are general functional motions. So in the figure on the right side, we have an unfolded protein on the left, and its folded states on the right, which have different interactions with water molecule, thus different surface hydrophobicity. It illustrates how protein hydration plays an important role in defining the structure of the protein and affecting its structural stability. So here we present a way to assess protein hydration alongside our secondary structure characterization in one single automated measurement. And the secret is what we call displacement factor. Let me explain. Here in this figure, the green indicates protein molecules, blue indicates buffer molecules. So the raw differential absorbance, or what we call the DFA, was obtained from a real-time background subtraction for the from the sample. So, however, the subtraction excluded the buffer displaced by the protein. The displaced buffer itself had absorption in the IR range. To obtain the absolute AU, the absolute absorption units, the displaced buffer absorbance has to be added back to the raw DFAU. So the displacement factor is used to add back this amount of over-subtracted buffer molecules, and it therefore represents the increase in volume upon the addition of protein to a solution. So the software will start with nominal displacement factor to find the best mathematical fit. So it is not the same, but very well correlated with partial specific volume, defined as the increase in volume upon the addition of 1 microgram of dry protein to a solution. So in summary, a typical trend is when we have increased surface hydration, in which case an increase in surface hydrophilicity or decrease in surface hydrophobicity, we will have a decreased displacement factor. So here we see a trend of decreasing displacement factor with an increasing sucrose concentration. And this suggests that sucrose has the effect of enhancing lysosome surface hydration and increasing its hydrophilicity or lowering its surface hydrophobicity, which usually relates to an increase in stability. And this agrees with what we would expect with the increase of sucrose concentration. Then with this tool, we can easily see how other factors affect protein hydration and surface hydrophobicity, like oxidation, temperature, etc. So in addition of all the standard things you are getting out of MMS also gives you a free data on protein hydration or protein surface hydrophobicity, which greatly correlated to protein stability in the formulations. So thank you so much for sticking to the end of the video. I really hope you learned something new today, and please consider giving this video a thumbs up. Thank you. Bye-bye.